I'm going to show you another application of right triangles. So this is, you probably all view this as a box, but it's technically a rectangular prism. Okay, a prism has two congruent shapes that are connected with straight sides, and actually straight rectangular sides. So we would call this a rectangular prism, rectangular upper and lower bases being connected by straight sides. We're asked to find the diagonal length of this prism, okay? The diagonal length here, the diagonal is not cutting across one of the faces, it's cutting across this entire figure. So for example, it might go from this lower corner here to this upper back corner. And it's cutting all the way through this three-dimensional solid here. Or it could go from this front corner to this upper back corner, or it could go from this corner here to that lower back corner, but it is cutting across and through this three-dimensional solid, okay? So if you remember when we found the distance formula equation, we created right triangles. You know, we had a line segment like this, we made a right triangle like this, and we found the length of the hypotenuse basically, and we turned that into a formula. Similar kind of thing here. We have a diagonal length. You can make sides of a right triangle, and here's how you can do it. You can drop down a side here along this edge to the base, to that point right there, and then you can connect those 2 points there, and you can get kind of a sideways right triangle inside this prism, okay? And you can use that to find the length of this side, okay? Now, a couple of things. This side length here is 5, and it's a rectangular solid, so we know that that side length back there is also going to be 5, okay? We should be able to find this side length here. When I'm working with three-dimensional shapes, a lot of times I'll draw individual faces separately. So this base face here basically looks like this. It's a 3 by 4, okay? We are trying to find this diagonal length along here, okay? If you notice, that's really just the hypotenuse of a right triangle. If this is 3, this side over here is 3, okay? In this particular case, we have a 3, 4, 5 right triangle. Sometimes you'll have to do the Pythagorean Theorem on these, but not in this case. And so this length is 5, okay? Horribly not drawn to scale, okay? 5 should have been longer than those other two sides. But here's the point. We now have a right triangle in here with side lengths of 5 and 5. And in this particular case, you may notice, oh, that's an isosceles right triangle. That's a badly drawn 45, 45, 90 triangle. The hypotenuse is going to end up being 5 radical 2. If you didn't recognize that, no big deal. You could just say, hey, I'm going to take that triangle that's on the inside of my shape, and I'm going to apply the Pythagorean Theorem. So we've got a side length of 5 here. We've got a side length of 5 down there. It's a right triangle. 5 squared plus 5 squared is equal to c squared. You would get 50 is equal to c squared. And so c is going to be the square root of 50, which breaks down to be 5 radical 2. So for this particular one, the diagonal is going to be 5 times the square root of 2. But notice, it's really just a couple of Pythagorean theorems. It's making a right triangle inside your shape, okay? Let's try another example. Let me just do some totally random side lengths here. All right, so here's my solid. And let's say that we have a side length of 2 and 4 and let's say the height is 3, okay? Something like that. So we want to find the length of the diagonal, same thing. Draw in your diagonal across, cutting through the entire shape. You can make a right triangle using one of the sides of your shape. And so we get that right triangle right there, okay? So at the base, we need the diagonal of that rectangular base. That rectangular base is a 2 by 4, okay? And we're trying to find this diagonal that cuts across like that, okay? So we're doing basically 2 squared plus 4 squared, and we're taking the square root. And that's going to be the square root of 20, right? 4 plus 16, square root of 20. Okay, now, I really hammer the idea of simplifying your radicals. And a lot of you are like, hey, shouldn't you write that as 2 radical 5? You can, but I'm going to suggest that you leave it in an unsimplified form in this particular problem. And here's why, okay? If this edge is 3, that edge is 3, okay? Look at what we've got now. We have a right triangle on the inside of this shape. This right triangle right here. We're looking for its hypotenuse. This is 3, this is radical 20, okay? It's just a second Pythagorean theorem. So we're going to take 3 squared plus the square root of 20 squared. Just going to knock out the square root. and that's going to be equal to c squared. Okay, that's 9. Square root of 20 squared is just 20. Okay, so c squared is going to be 29. That means c is going to be the square root of 29. Okay, and that's our missing diagonal length. Square root of 29 doesn't break down, so you don't need to worry about simplifying it. Okay, one final example. I want to do a cube. There is a pattern for a cube. I think they're going to have you kind of delve more into that pattern in the book, so I may not go too far into here. But let's say that I had a 2 by 2 by 2 cube. Okay, and you can always draw some squares and connect them like this. So let's say it was a 2 by 2 by 2, and I want to find its diagonal length. So same kind of thing. Diagonal cuts through here. I can make a right triangle going back to here and going up like that. There's my right triangle. Okay, the base is a 2 by 2 square. Okay, which is really nice because we know that's a 45, 45, 90 triangle. The diagonal is going to be 2 radical 2. So we've got a 2 radical 2 on that side. This height right here is going to match up with that height. It's also 2. Okay, so what do I have here? I have a right triangle, the purple right triangle on the inside here, that has a height of 2, and it has a 2 radical 2 on that side. So we can take 2 radical 2 squared plus 2 squared, and that'll be equal to c squared. Okay, 2 squared is 4, radical 2 squared is 2, 4 times 2 is 8, plus 4 is c squared. C is going to end up being the square root of 12, which is 2 radical 3. Okay, there is a pattern, there is a formula for a cube. It doesn't work for other prisms if they don't have the same dimensions. But if all 3 dimensions are the same, there is a formula. Notice we have sides of 2, 2, and 2. We have a diagonal of 2 radical 3. That doesn't prove any kind of pattern, but it is one example of the pattern. Okay? In another video, I'll probably show you the proof of that. But anyway, that's how you find lengths of diagonals of prisms using right triangles.